And I hope that the full screen mode is also visible.
Correct. It is.
Fantastic. Thank you. Thanks, everyone. Thank you, sir, for having me again. I'm happy to present a first of its kind AI-led public transport concept that we've developed at the Ola Mobility Institute called ATOM, Autonomous On-Demand Mobility. Like Sir just mentioned, I had research at OMI. We carry out research on 5 areas: electric mobility, energy, urban mobility, accessibility and inclusion, and future of work and platform economy. Through the course of today's presentation, I will help you walk through the evolution of public transit. We will gain an understanding of ATOM, the concept that we've developed at OMI, cover its advantage, and list ways through which India and the world can revolutionize public transit by adopting ATOM. As we all know, public transport is the primary mode of road transport for most Indian citizens, and India's public transport systems are among the most heavily used in the world. There is a quick overview that I'd like to present of the public transport's journey in India, beginning with trams. Trams, first established in the late 19th century, were discontinued though in all Indian cities between 1933 and 64, except for Calcutta. The first public bus service was operationalized in Mumbai in 1920s. Today, Mumbai's BEST is India's oldest operating transport body. Undoubtedly, state-run public bus services are the mainstay of public transportation in Indian cities. They provide low-cost mobility to masses through subsidies offered by the government. In 1984, India witnessed the launch of its first metro rail in Kolkata. In 2002, the Delhi Metro was launched. With rapid urbanization and an ever-increasing demand for providing sustainable urban public transport, metro is now the preferred investment, as we all know, for mass transit in Tier 1 and Tier 2 cities. India has over 700 kilometers of operational metro lines in 18 cities and over 1,600 kilometers of metro lines under construction in 27 additional cities. In 2006, the first bus rapid transit system was launched in Pune. Cities also have at-grade bus rapid transit system, light rail transit system, and monorail as alternatives to the metro. Some have operational BRTS as well, but the coverage is limited, of course, due to the exclusive right of way that such transit services need on city roads. Public transport is also undergoing further development with driverless metro implemented in select cities, Metro Line and Neo being planned in various parts of the country, and newer innovations like Hyperloop and passenger pods being conceptualized but yet to be implemented. At the same time, there are a few problems common to these public transport modes that ail these mobility solutions. One of them is obviously high capital investment. Metro rail projects are capital intensive. The operator has to bear the entire cost of civil infrastructure, rolling cost, and operations and maintenance. Road-based transport operators, on the other hand, only bear the cost of rolling stock, operations, and maintenance of vehicles. The second issue is high construction time and delays. Delayed or extended construction time adds to the opportunity cost associated with metro projects. The normal construction time for metro projects is 5 years. However, problems arising out of land acquisition, financing, rehabilitation, and externalities associated with project management lead to delays in construction. The third issue is poor financial health. Public bus services are currently financially unviable in India. We may all know the combined loss of SRTUs for financial year 2015-16 was to the tune of over 11,000 crores. 40 out of 47 SRTUs have incurred losses, whereas only 7 have reported profits. Intercity operations are profitable as compared to intracity operations and compensate for losses to a large extent. Furthermore, in metro projects, the accuracy of traffic demand projection often significantly determines its financial viability. Studies find that most of these projections are inaccurate. The next challenge is also poor operational efficiency combined with low ridership of mass transit solutions in the country. Ridership also varies significantly between peak and non-peak hours, reducing the occupancy ratio of public transit modes. The variations in occupancy between peak hours and non-peak hours is significantly high, thereby leading to low operational efficiency due to fixed costs such as fuel and other overheads. Further, cities face numerous challenges in developing an optimal network of public transport, connecting residential and business districts. In this context, first and last mile challenges to and from metro stations and other modes of public transit too are nearly a universal concern. In this backdrop, can shared, connected, electric and AI-powered mobility, all of which are regarded as the new paradigms of mobility the world over, can these four paradigms address the problems faced by public transit with a single solution? It is here that we present ATOM, a concept developed by the Ola Mobility Institute. ATOM is short for Autonomous On-Demand Mobility. ATOM is a first of its kind AI-led public transport solution imagined for India and the world. It is an artificial intelligence-based public transport concept to provide demand-responsive service in cities through access-controlled roads. We'll see what each of these mean in the real world. ATOM is a concept at the intersection of shared, connected, electric and AI-powered mobility, and it is being presented as an alternative to metro rail and bus rapid transit system to provide equitable, viable, clean, efficient and demand-responsive public transportation for all cities. So ATOM is an integration of various bus-like vehicles called NEOs. You see one envisaged model of a NEO in front of you. NIOs or native intelligent operatives run on lithium-ion batteries and are fitted with various components to enable a driverless and synchronized operation. NEO thus includes GPS, LiDAR, light detecting and ranging sensors, radar sensors, cameras, central computer, infrared sensors, Li-ion battery pack, of course, and a portal for EV charging, among others. ATOM has an AI platform that makes decisions based on inputs from vehicle sensors, control room inputs, and accordingly sends signals to the actuators such as steering, braking, and powertrain to ensure vehicle movement as per assigned routes, speeds, and frequency. As you can see, there is an interaction between the control room and NEOs through V2X communication. The V2X unit on board the vehicle enables communication between vehicle to infrastructure, and vehicle to network. The V2X unit uses dedicated short-range communication, which is a one-way or a two-way short to medium range wireless communications to talk to and inform each other about the surrounding environment. Then lastly, there is the depot for ATOM. A depot consists of operations and control center, EV charging infrastructure, parking bay, and vehicle repair and maintenance center. The NEOs that you see here move to the charging base automatically when low on battery. This is within the depot, and all of this movement is managed by the onboard AI platform and the control center. The major differentiating factor for ATOM vis-a-vis other public transport modes is that it is able to platoon on the basis of demand. We commonly refer to this as virtual platooning. Virtual platooning enables NEOs to operate in various configurations and sizes dynamically to optimize occupancy and improve operational efficiency. Thus, NEOs that you see on the screen can operate in configurations of 1, 2, or 3 depending on the demand for ATOM. Additionally, a single floor design with space optimization for standing passengers is what we would recommend to improve carrying capacity of ATOM. ATOM is further conceptualized in 3 variants. The first variant is HATOM. HATOM has the highest passenger capacity, catering to high traffic corridors with a maximum peak hour peak direction traffic of 40,000. NEOs move, in the case of H-atom, NEOs move on a guideway, which is an elevated viaduct to enable higher average speed, less disruptions due to regular traffic, and operation of higher capacity vehicles. This guideway, as you see on the screen, will not require any additional land acquisition. The second variant is M-atom. M-atom has medium passenger capacity with a maximum PHPDT of 16,400. NEOs move on an at-grade access-controlled guideway at the center of the road with flyovers or underpasses at traffic intersections, thus enabling a higher throughput of passengers and avoid any interface with regular traffic. The third and the last variant is L-atom. L-atom has low passenger capacity with a maximum PHPDT of 12,500. The L-atom guideway is an access-controlled at-grade roadway that's capable of interacting with regular traffic at intersections. The traffic signals should have the facility to communicate with NEOs through vehicle-to-infrastructure communication protocols. We then at OMI compared the different variants of atom that we were developing with different forms of public transportation and tried to understand which could be a more financially viable solution for public and the private sectors combined. So the following slide, this slide precisely on the screen, gives you that comparison. For H-atom, we analyzed an 18.5 kilometer elevated corridor of metro and compared it with implementation of H-atom. H-atom in this analysis revealed that H-atom has high capacity, like I mentioned, with 40,000 PHPDT. The capex cost of H-atom in this case of comparing it with a metro of 18.5 kilometer elevated corridor with 19 stations is fairly lower than metro by at least 48%. Construction time for H-atom is lesser than that of metro by at least 50%. Internal rate of return for H-atom varies from 63% to 8% depending on government investment in civil cost and meeting traffic projections. Because all forms of atom are conceptualized as being demand responsive and because of the other factors that I just mentioned, H-atom, just like M-atom and L-atom, is operationally more efficient compared to a metro rail. We further analyzed a 20-kilometer route of BRTS and light rail with 25 stations each vis-a-vis implementation of M-atom. This analysis revealed the following. M-atom has medium capacity, like I mentioned earlier, with 16,400 PHPDT. M-atom is cheaper than light rail by close to 60%. It is only 20% more expensive than BRTS. It is operationally more efficient than both BRTS and light rail. It has 1.7 times passenger capacity of BRTS and 1.4 times that of light rail. Lastly, the same comparison of L-atom with BRTS and light rail revealed that L-atom too is more financially and operationally efficient. A reminder that L-atom is the variant of atom with low capacity having 12,000 PHPDT. L-atom in this comparison was found to be cheaper than light rail by 64%. L-atom costs the same as BRTS. It is operationally more efficient than BRTS and light rail, and it has 1.3 times passenger capacity of BRTS and 10% more than that of light rail. Atom thus offers benefits to every stakeholder in the mobility ecosystem. To the government, it offers more than 50% reduction in capital investment. It offers nearly 50% reduction in construction time. Atom promotes public-private partnership in public transportation. It has zero operational expenditure and investment for the government. Atom has high service levels, improving commuter experience and thereby for a city as a whole, it can attract more people back to the sustainable mode of transportation, which is public transport. To the private sector, Atom has a large market potential and offers opportunity with applicability in 60 plus cities in India. And this is, 60 plus cities in India alone, and therefore has a lot of potential outside of the country as well. To the private sector, Atom is also a viable investment option with a high internal rate of return. It helps increase global competitiveness of India's businesses, adopting futuristic technologies. Atom provides opportunities beyond public transportation. Atom, for instance, has the potential to revolutionize freight transport on access-controlled highways, intra-terminal transportation, and passenger transportation in large commercial and residential spaces. It can unlock higher investment value by opening up an all-new market for AI-based mobility in India. Lastly, to the commuter, Atom provides affordable public transportation, real-time information, predictive journey time, and therefore is demand responsive, a service ensuring high service quality. Atom is further digitally, or it can be digitally integrated with first and last mile connectivity solutions as well as digital payment solutions. We envisage that Atom can be effectively implemented to provide public transportation in cities like Agra, Lucknow, Kanpur, Surat, Indore, Bhopal, Coimbatore, from where I come from, and even Chandigarh. All these are cities where metro is currently being planned or under construction, and the traffic projection for 30 years is under 40,000 PHPDT. Further, cities like Delhi, Bengaluru, Kolkata, Hyderabad, Chennai, Mumbai, Pune, and Nagpur with existing metro rail networks can also adopt Atom. Atom can provide feeder or complementary service on low traffic routes. Feasibility studies can be undertaken for each of these cities by potential investors in Atom. In cities like Gorakhpur, which has 28 kilometers of metro, Surat, which has 33 kilometers of metro, and Visakhapatnam, which has 42.5 kilometers of metro, each Atom can save anywhere from 2,500 to 5,000 crores compared to the metro projects themselves. Thus, Atom is a concept that we've developed at the intersection of shared, connected, electric, and AI-powered mobility. It is a cutting-edge concept for the world. It is envisaged as a demand-responsive service through dynamic platooning. It is digitally integrated with first and last mile and payment solutions. It makes public transit more efficient and affordable. It offers high internal rate of returns and provides financial viability to public transit. It is an equitable, viable, clean, and efficient mode of public transit for India and the world. The Atom transportation mode that I've just presented offers savings on capital costs, reduces construction time, like we just saw, provides higher capacity utilization, is demand responsive, and is more efficient than than many of the existing public transport modes. Additionally, Atom offers benefits in terms of demand responsiveness and seamless commuting. I think overall, Atom is being presented at this forum as an open source concept to stoke the imagination of various stakeholders. And these are not just limited to the private sector operators, OEMs, or technology companies, but also universities, government agencies, and commuters. Inspired by the successful model of public-private partnerships in airports, it is recommended that the infrastructure for Atom be provided as a service by the government. This is where the concept of Atom as a service model too could be developed. This would allow for the private sector to manage operations and maintenance while paying a user fee to the government for infrastructure. Some of this can also be seen in the world of intracity bus services, and such PPP models could be scaled extensively. Atom requires the integration of elements such as rolling stock, artificial intelligence, electric vehicle technology, civil construction, and high-value components like sensors, radars, actuators to enable autonomous driving. Transforming this concept into reality would require coordination among various stakeholders who are specialized in individual components of the technology or as system integrators to put the building blocks of Atom together. This is being developed simply because we don't want India to lose on the larger race of, or rather lag behind on the larger global race of innovation, of embracing artificial intelligence. And we certainly feel that something like Atom can propel India to the global stage. With that, I conclude my presentation on Atom. Here are my coordinates in case you'd like to get in touch. Thank you so much.